we're going to talk about minimizing finite state machines. And this topic won't take the whole day, and then we have a little bit more to do afterwards, and that will finish the material on finite state machines. And the next lecture will pop up and talk about the next layer on top of it. We'll glue on a new piece of power and make finite state machines something that really can do more. But right now we're still at this basic level, and one of the fundamental nice things about finite state machines is that if you create one, then you can minimize it to a unique finite state machine. So if everybody's got a different finite state machine for a particular problem that I gave out in class, you could all minimize that, and when you were all done minimizing it, you would all have the exact same machine. So that's nice. It's a nice feature. It's clean. It's simple. That's not true for Turing machine programs, and it's not true for the middle level, for push-down machine programs. There's no minimum machine in those levels, and here there is. And the presence of this minimum machine really lets you understand finite state machines really well. It's at the core of doing a lot of the, what we call, and what we'll talk about at the end of the day, decision algorithms about finite state machines. Questions about them. What do you know about them? A lot of it's helpful by being able to minimize it. All right, so to explain this idea, I want to go off on a little tangent. And I hope this will give you the intuition behind it. And then I'll go into it very, very much in detail and do at least 2 or 3 examples to make sure it's all clear. So here's the intuition. You're stuck in a cave. And this cave has rooms that look just like a finite state machine. Rooms with little doors out of the rooms. And the doors are marked like 0 or 1. You know, so in a 0 you go through this door, and a 1 you go through that door. And you don't have any map of this cave. All right, so somebody just transports you into one of the rooms, and you look around, and you see a 0 on this door and a 1 on this door. And you want to map the cave. You got a little piece of paper and a pencil that writes on this piece of paper, and you want to kind of make a map because it turns out that there's water in some of the rooms in these caves, or food, or good things, and other of the rooms don't have good things. And you want to be able to figure out which rooms have good things, which rooms don't have good things, and be able to get back and forth from one to the other without getting lost. All right, so how do you do this? What do you do? Have you ever played like these Dungeons and Dragons games from many years ago, Adventure or Zork or any of these things? No, you have, right? No. All right. What am I talking about? All right. Well, anyway, in these games, you often find yourself in a maze like this. And what you basically do is exactly this. You take a piece of paper and you map out the maze so that later on, when you're running through the program, you can figure out where you are. Otherwise, you can't tell from the description of the program where you are. So it's the same thing. You're stuck in this cave. What do you do? So you walk around. You go through, you write, you make a little circle. And now you walk out the door. You walk into another completely nondescript room. And you say, OK, now I'm in this room. And then there's a door with a 0 on it. And you walk into another room. Right? How do you know if that room you walk into is this one, or whether it's a new one? You don't really know for sure. You have no idea where these paths go. No sense of direction. No sense of up or down or back and forth. So when you're all done making this map, number one, you can go on to infinity until you suddenly start to notice a pattern and say, oh, gee, I think the room I have here is actually the same room as I wrote over here. They're really the same thing. I really should just collapse those together. What you tend to do is you can create this huge map which is much bigger than the real map, but which works just as well because it's still consistent. It's just that you have 2 circles on there that represent the same room. You might realize this after you walk around in the cave for a while and collapse your map and make it simpler. Right? So this complicated map is like a finite state machine that isn't minimized. And this real map, which has every room have really just 1 circle, that's the minimum finite state machine. If you keep that intuition in mind, you'll really get this idea, I think, more quickly. All right, so with that idea in mind, let's do an example. All right, I like this example. Now, some of these examples you're going to be able to eyeball and see how to minimize. And that's good and bad. Good because it'll give you the intuition, but bad because you might not see the more general algorithm. So we wander around the cave, and we come up with this map. And in these two rooms, there's good stuff. There's food and water or treasure. And now that we've got it all written down, we're going to sit with a piece of paper and our algorithm and our smartness and minimize this, just in case we happen to have two rooms that are functionally identical. What does it mean, functionally identical? Well, I'm going to point out two states that couldn't possibly be identical. The only states that you know can't be the same right now are like one of these that are circled with the food and water in it, and one of these that doesn't have food and water in it. You definitely didn't confuse those. Either there's food and water in the room or there isn't. So if I label these states, A, B, C, D, E, F, some pairs of these states are already distinguishable as being different, and some you're not sure whether they're different or not. And what does different mean? We have to say what it means. Well, by definition, final and non-final states are different because one has the good stuff in it and one doesn't. You can't possibly merge these together and keep the same functionality of the machine. They're distinguished automatically. But what about other states? Let's say, here's a good one. A lot of these states are not distinguishable, so it's hard to say. Let's say C and D. From D, we're going to move into here on a 0, and we would accept that string. From C, we're going to move into here on a 0, and we would accept that string. What if that held for longer strings? What if no matter how many symbols I started looking at from D and how many symbols I started looking at from C, that whenever I accepted for D, I also accepted C, and whenever I didn't accept D, I didn't accept C? Then what's the point of having two different starting places? I might as well merge these into one place.
But they didn't go to the same cell. They just both went to accepting
right.
states.
Right, but that's all we care about as far as the finite state machine is concerned, is whether we accept these strings or not. So if all we want to know is whether we're going to accept a string, if all the strings from D and all the strings from C both get accepted or rejected the same way, then there's no reason to have them be different places. We might as well start them at the same place. So that's what we're going to try to do. We're going to try to indicate which states are like that and which states aren't. We can experiment a little here. I mean, is it true that D and C are equivalent? Does it happen to work that way? Let's try a couple others. Say a double 0. 0, 0 ends up not accepting. From here, 0, 0 ends up not accepting. Can you come up with any string that distinguishes D from C? Are they really the same? And if they are, we have to rigorously figure out how we're going to decide this. We can't just eyeball it. But right now, let's just eyeball it.
So the arrow going from E to C doesn't make a difference?
Doesn't make a difference as far as distinguishing D from C?
Yeah.
Well, maybe it does. But the way to determine whether it does or not is whether you can find me some string that when I started from D and C simultaneously, they end up doing different things, one accepting, one not accepting.
So anything that goes DEC would go CDF just as well. And C and F are very symmetrical.
When you think about it this way, A is distinguishable from E on a very short string. On what string is A distinguishable from E?
Empty string.
On the empty string. If you don't see any string, then here you accept, and here you accept, and here you don't accept. So that's why the final and non-final states are distinguishable one another. They're distinguishable because of the short empty string. If you read an empty string here, you don't accept. If you read an empty string here, you do accept. So they can't be the same place. All we got to do is keep bumping this up. We start with empty strings to distinguish states. Then we go to single symbol strings that distinguish states. Then we go to 2 symbol strings that distinguish states. Then 3 symbols. Then 4 symbols. It turns out that if you're going to distinguish 2 states, in this machine with 6 states, if you can distinguish 2 states with a string, you can find a string that has 6 symbols or less to distinguish it. Because after that, you'll get a loop, and you can always find a shorter string to distinguish it. So we actually don't have to go forever looking for these strings to distinguish states. We just have to go up to strings of length 6. So that's a mechanical, brute force, horrible procedure, and there's a lot of ways to do it. And I want to talk about how we're going to do it in as efficient way as we can. OK, questions about this?
Analogy, you could, it doesn't really hold, does it? Because if you eliminate, if you have your big map and you eliminate 2, you could actually they could be different places in the cave and still functionally the same.
Yes, it's possible in a cave to actually have 2 different places that happen to really do the same things. But it's also possible that they're the same place and you never noticed.
That's right.
That's the key. The key is that in a cave, you could build 2 rooms in a cave that have the same functionality as far as the paths go. But the reason I gave you that analogy at the beginning was because I wanted you to imagine that you didn't know what the cave looked like. And this was your map of the cave. And it's completely possible that your map of the cave is misguided, that you actually listed the same room 2 or 3 times. In fact, these 2 states, 2 states with water and food in them, maybe this is the same room. Maybe when you went out the door for one, you actually went back into the same room and you never noticed. In fact, that very well might be the case. So that idea of making a map and looking for the underlying structure, I think, is a good one to keep in mind. But if it doesn't help, then forget it. I mean, just think about finite state machines.
Why is it 6, length 6 instead of 5? Because in 5 we've gotten every state.
It might be. You're saying, why do we have to go all the way up to 6?
Yeah.
It's possible you'll get a string. It's possible that maybe you only need 5 to distinguish. I have to think about that. I'm not sure, Peter. But there is a limit as to how far you'd have to go. OK. So here's what I'm going to do right now. And then I'm going to do this in a little more of an algorithmic way. Here's what I'm going to do. I'm going to describe what we have to look at in this picture to see whether one state is distinguishable from another. And the base case, or the beginning step, is that all the non-final states are distinguishable from the final states. So here's what I'm going to do. I'm going to make a different picture on this side of the board that represents the dependencies or the distinguishing states here. There's going to be a lot of these. Maybe there's going to be too many, so I might. How many are there going to be? 6 times 5, it'll be like 30 boxes. It'll be too big. I'll just make a simpler picture. A, B, C, D, E, F, E, D, C, E. This is supposed to represent a combination of every state with every other state. And we're going to say whether they're distinguished one from another.
And why aren't all 6 of them in each of those columns?
Because you'll see in a second. You'll probably figure it out.
It doesn't matter.
I don't. Right. I just need to consider all 30 combinations of these pairs of states. It's 6 choose 2. So I don't want to consider anything. I mean, A and B is the same as B and A. I just list them in an order so that I get every single pair once.
So there's only 15.
No, there's, oh, is there?
Yeah, 15 pairs.
Oh yeah, 6 choose 2 is 15. Yeah, thanks. Right. Right, there's only 15. All right, so I'm going to make x's in the squares that the states are distinguishable one from another. So where do I make x's? A is distinguishable from what? From B and from E. B is distinguishable from
True, but what's going on?
I'm putting x's in all the squares that represent pairs of states that are distinguishable one from another. So all the final states and non-final states are distinguishable from one another. And I'm putting x's in those squares.
I guess you're just going about it differently than I was thinking. Go on.
Okay, well, tell me where the rest of the x's are. Good. There's one here, right? And one here and one here. Okay? All those x's represent the combinations of final states and non-final states. States that we know are distinguished one from another. What we'd like to do is just fill this chart in. If we can fill this chart in and decide which states are really distinguished one from another, then we can collapse the states that are indistinguishable into one. That's the idea. So if it turns out that B and E are the same, we will later on turn these into one big state called BE. And they'll just have one circle. If it turns out that A and C are the same, we'll collapse A and C together.
Is the start state always different from every other state?
No. No. It's a good question. And let's hold off on why for a minute. But you'll see. OK, well, let's go through. Let's do something very naive. Let's just take these blank squares that we don't know whether they're distinguished one from another and try to determine it. A and F. How would you decide whether A and F are distinguished from one another? Well, the base case doesn't work here. They're both non-final states, so they either are distinguished from one another or they're not. We don't know. So let's try to refine our information here by adding in a single string, a single symbol that starts in A and F simultaneously and see where we end up. Let's look at the 0 coming out of A and F. Where do you end up? B and E, respectively. And let's look. Are B and E distinguishable? Where's BE in our chart? Not distinguishable yet. Now, if B and E were distinguishable, then what would you have known about A and F? That they're also distinguishable. Okay, if A and F each have a 0 that go to distinguishable states, then A and F are distinguishable too, because you just tack that 0 on whatever string distinguishes these two that you ended up in. Unfortunately, they don't go to distinguishable states, they go to BE. But
So you can get to F from a terminal state, whereas you can't get to A from a terminal state. Is that enough to distinguish them? B goes to F, and B is a terminal state.
that's not enough to distinguish them. Right. That would not imply that there's a string starting in A and F that would give you different results. It's a good question.
So even if they're both final states, if they've been shown to be distinguishable somehow, then the things that point to them are distinguishable.
Yes, sure.
Even though they both, if really all we care about is acceptability, then they're similar in that they would both accept that string. If those final states are distinguishable from one another, then...
But if the final states are distinguishable from one another, that means that starting here, you can come up with a string, and using the same string from here, this one follows that string and gets accepted, and this one follows that string and gets unaccepted. So it's very important, even though they both go to final states, if this one goes to this final state and continues with that particular string, and this one goes to this final state and continues with that same particular string, the resulting string would not agree. So you wouldn't want to merge those two, even though they're both final. Right? So again, it's not where you end up, it's where you go from there. That's another good question. All right, well, let's look at the other symbol. What about 1? On a 1, you go to D, and C and a 1 you go to F. And are D and F distinguishable?
F to C. We're looking at,
Oh, sorry, F. We're doing A and F, so it's D and C. Are D and C distinguishable? No. So we have not now determined that A and F are distinguishable. As far as we know, they're still undistinguished. They still might be the same. However, if later on in this process we find out that D and C are distinguishable, then what should we do?
Go back and make AF.
Then we should go back and put an X in AF. In order to do that, here's how the algorithm actually works. You go into, let's do the 0 first. 0 ended us up in B and E. Go into the BE state right here and put in AF. And if we ever get an X in here, we're going to go back to AF and put an X in there too. We'll also put an AF in what pair of states? In C and D, where you go on a 1 from AF. So in CD, which is here, we'll put an AF. This means that later on, we're going to go through this row by row. Later on, as we hit these two states, if they end up having an X in them, we will backtrack and fill an X there. This backtracking can wind up. If there was some letters here, we'd backtrack further up. But this was the first one, so there's no backtracking. All right, let's continue. We're going to go through the whole set of empty squares, one at a time. And when we're all done, we'll have all the dependencies looked at, and we'll have a sense of whether these states are distinguished or not.
Just checking single length one string.
Yes. Yes.
And that's enough? Or?
Yes. And it's not obvious it's enough, but it is enough. I'll try to explain why it works later. I think it's better for me to do how it works first. And it is going to be enough, because really what's going on, this is a single length information, but later on, if we find that these are distinguishable, and then we go back and make that distinguishable, that was distinguished thereby by a double symbol. So the amount of your backtracking is the size of the string that distinguishes it. So you can't have backtracking more than 1, 2, 3, 4, I guess 5 is the longest backtrack. So that's what you asked before. Let's go on. What about AD? What does that depend on? AD, what does it depend on? What does the distinguishing characteristic of AD depend on? It's distinguished if what other states are distinguished? AD is distinguished if BE is distinguished. So I'll put a dependency line here. This graph has nothing to do with a finite state machine directly. It's not a finite state machine. It's just representing these dependencies so everybody can see what's going on. AD depends on BE through 0, and AD depends on AD with 1. If you ever get something that depends on itself, you don't bother writing in AD to itself, because that's never going to happen. In fact, when you see this happening, as far as you're concerned, that part of it says that these two states are indistinguishable. As far as the 1 is concerned, they might as well be the same state. It depends on itself. It's never going to get distinguished. But it might get distinguished if B and E get distinguished. So let's go to BE and add AD in to that list. And now let's continue on with AC. What does AC depend on? It depends on BE again. And what else? AC. Oh, just BB. Whenever you get something like this, that means both states went to the same place. Those are automatically indistinguishable. So it certainly does not distinguish AC. These pairs never get X's on them. They're automatically empty. What else does it depend on? And DF. Where's DF? Here. So what goes here? AC. So we don't know if any of these will end up being distinguished. Right now, where they're not distinguished, it depends if one of these get distinguished later. And now we're just going to continue on to the second row and look at BE.
look ahead for a second. Where are you going after you get this?
When I'm done looking at all these empty squares, and I'm finished backtracking all the x's, then I'm finished. And at that point, I'm going to look to see how many x's I have. And based on what the x's are, I'm going to collapse this picture down to a simpler picture, making all the states that are indistinguishable from one another into a single state. There's really a lot of math behind this that I'm leaving out for a minute, but I'll just briefly mention that this is based really importantly on this idea of an equivalence relation. Deciding whether one state is distinguishable to another is an equivalence relation. And the reason that's important is that when I'm all done, I don't want to have A, C, and F equivalent to one another, and also have D, C, and F equivalent to another, but have A, D be different. That would be crazy, because then I couldn't collapse it. I'd have to collapse A, C, and F to one state, D, C, and F to another state, and somehow leave these independent. So when we're all done doing this, if you have any three that are all the same, and then some subset of them are the same with another one, then that one is the same as this one too. It's an equivalence relation. It's transitive. So you never get a problem with collapsing it, and you'll see that at the end. But your question about where we're going is important. When we're all done, we're going to collapse it down. And we can collapse it down because it's all an equivalence relation. All right, where are we up to now? BE? Okay, so who can do this? Who's not afraid to try? Depends on CF. Why? Because B on a 0 goes to F, and E on a 0 goes to C. Depends on CF. And what else does it depend on? Depends on itself. So we go to CF, and we write in BE. Now we're going to go down to this CF. If this gets an X, we're going to go back to here and put an X in. And we're going to go back here and here and put X's in. Right? We've got a lot to do if any of these get X's. If they don't get X's, then they're still indistinguishable. So let's go to CF and see what happens. Let's actually just leave it from here. CF, what does it depend on a 0? Depends on BE. What does it depend on a 1? You see this funny graph? It's not a finite state machine. It's a graph. It's a directed graph. It represents something. It's something really important. It represents the dependencies of the pairs of states on each other. The vertices in this graph are pairs of states. The edges are, there's an edge from here to here if this pair is distinguishable makes this pair distinguishable. So CF depends on BE. What does that mean? We're not going to go back here and put CF in this line, because that's a cycle. We never go back. We go forward and put things in, but we never go back. Going back means we found a cycle, and it means we're not ever going to get a distinguishable characteristic. So we leave that, and we move on to CD. What does CD depend on? BE, right? What else? Well, AF is back up farther up, so we're not going to put anything there. And BE is farther back, so we're not going to put anything there. So we move on. Still nothing distinguishable. Now we're going on to DF. DF. DF depends on a single E. That's indistinguishable. Don't get anything from that. And it depends on AC, which is further back up there. So we ended up finding nothing but all these cycles of dependency, none of whom were dependent on any of the things that had X's in them. So we hit this last one and it's done. We are done now with the algorithm. What this shows is that the only distinguishable states in this picture that we started with were the ones I started with. We didn't pick up any on the way. I'm going to do examples where we do pick up a lot along the way to show you that later. But this time we went through, we picked up nothing on the way. Let's finish it up and rewrite this picture. I'll talk a little bit more about the this funny graph, about how the thing works, and then we'll do 2 more examples. Let's fix this picture to make it minimum now. The only states that are distinguishable are the ones here with x's in them. That's the only pairs. That means all the other ones are the same. That means A and F are the same. Let's write that. A and F are the same state. A and D are the same. So I add that to the list. F and D should also be the same. Remember, this is an equivalence relation. It's transitive. If A and F are the same and A and D are the same, then F and D should be the same. It is. If there had been an X here and no X's in all the other words, it means you made a mistake. You made some error. If AF and AD are indistinguishable, then so are F and D indistinguishable. And AC is indistinguishable. So there we have AF, DC, all indistinguishable. We've checked this one, we've checked this one, we've checked this one. How about this one? Checked it. Checked it. We haven't done this one yet. Have we done this one? Yeah. So this becomes another separate state. It's this. You see this? This is one class in the equivalence relation. This is another class in the equivalence relation. All of these are indistinguishable one from another. All of these are indistinguishable one from another. But they are distinguishable, this class from this class. And if you remember back in discrete math, equivalence relations partition their elements into disjoint sets. And that's what this is doing. So we only have 2 legitimate states in this machine. One called BE and one called AFDC. Let's rewrite this machine. Here's AFDC. Do this just like the non-determinism trick. If you're an AFDC and you get a 1, where do you end up? You end up in the same set of states. If you're an AFDC and you get a 0, where do you end up? In the other set of states. If you're in BE and you get a 1, you stay here. And if you're in BE and you get a 0, you go back to the other set of states. So this big ugly machine is really just what? Odd number of zeros. If I just show you this at the beginning of the class and I say, oh, here's a little puzzle, what does this machine do? I don't think anybody in 10 seconds would say, oh, it's an odd number of zeros, except maybe one of you on a good day. But if I show you this one, probably every one of you would know within a few seconds that it's an odd number of zeros. It's a lot better to work with a minimum finite state machine. When you're defining an architecture for a computer that you're building, you have a big finite state machine that represents the microcode and how it's all going to be distributed. This opcode do this. This opcode do that. This symbol do this. And you want to just define it without worrying about minimizing it. So you define it, you make it nice and clean, and then when you're going to really implement it, and when you want to turn it into hardware, and you want it to be small and compact, then you minimize it. So it's a very commonly used algorithm, and you need to do it. Are there questions about this so far? There's a lot more I need to say and more examples I'll do. But questions about this example so far? Heather?
Just a comment. I learned how to do this another way originally, so if anyone wants to know a different algorithm.
Completely different?
Pretty different, yeah.
Okay.
There must be like little patterns of little machines that you just look at and know that that's not unique, right?
You can certainly eyeball it and save yourself some of the trouble, but this the machine can do. Yeah. Yeah, Mike?
Sorry, is there any significance of the fact that the little grid that you had is kind of symmetric about the diagonal from like upper left to lower right?
Only because this machine is completely symmetrical. Otherwise, there's no significance. Yeah. I mean, this machine is just all, you can fold it on itself in every direction. That's why.
You see that, like, you know that you automatically know?
No. No, it wouldn't imply anything, right? Before I go on to the next example, I want to talk a little bit more about this dependency graph and how it relates to knowing which states are distinguishable one from another. Here's part of the dependency graph. BE depends on itself and depends on CF. CF depends on BE and depends on itself. CD depends on BE and depends on AF. let's fill in a little more of this and try to get a sense. AF, let's just put in some more things. What did AF depend on?
E and D, E, C.
Depends on CD, right? And what else? And BE. Where are the states that are distinguishable? They're not in the picture. Let's put some in. How about AB? That's got a big fat X on it, right? That pair is distinguishable. They are different, A and B. Is there anything that we did in this diagram, any of the open boxes, any of these guys, that ever depended on AB or any of the states with X's in that? They didn't show up at all. If they had shown up, we would have propagated the X's back, but they didn't. This dependency graph is going to be pairs of nodes, all dependent on each other, but none of them actually connect up to these X's. AB, CB has an X on it. All these states with X's on them are sitting there disconnected from this graph. What you're really trying to do in minimizing a machine is you try to construct this dependency graph, start from the X's, and go backward on the arrows and see what you can reach.
So there are dependencies within that site, within that graph, right? Like
what does AB depend on?
Depends on DE, for example, right?
AB depends on, let's write it in.
So they're just not connected.
It'll never connect to this part. What I want you to think about is this. If I give you a finite state machine, you can make a picture of this graph. You can make a computer make a picture of this graph. The nodes are pairs of vertices, and the edges are whether they're dependent on each other by single strings. If you want to figure out whether they're dependent on each other by more than a single string, you just follow a path of length 2. BE is dependent on CF. CD is dependent on BE. So CD is dependent on CF by a string of length 2. All you have to do to figure out whether one state is dependent on another is to take these X's and flood them through the graph backward along the arrows and see what they can reach. Anything they can reach should get an X. Anything they can reach is also distinguishable. Now, what kind of algorithm is that? You're given a graph, a directed graph. Some of the nodes are marked with X's. They're marked. All you're supposed to do is start from there and see what else you can reach. How do you do that? Right, depth first search, or breadth first search, or any kind of search that goes through a graph. How many steps does it take to do that? It takes time proportional to the edges in the graph. How many edges are in this graph? There's 2 edges out of every single node. How many nodes are there? If there's n in here to start, if there's 6 here, there's 15. If there's n here, it's n choose 2. So the total number of edges in this graph are 2 times n choose 2, which equals n times n minus 1. So the time it takes to do this algorithm should be no more than n squared. You should be able to construct this graph and traverse it in n squared and look to see where the x's propagate. And that's exactly what this very peculiar thing is doing. This is really traversing the graph forward, starting with things of length 1, looking for things of length 2, and if it says CD to BE, does BE have an X on it? No. But if later on BE gets an X on it, I'll propagate that back. It's kind of a twisted way of traversing through a graph. That's all it really is. And the reason why it's done that way is because in this graph, you can find out whether CD depends on BE, but if BE gets an X, you have to push the X through on the backward arrow. So you're not given the graph in the normal way. You're given it with the backward arrows. Therefore, we kind of traverse it as we get it, leaving little crumbs to backtrack rather than doing the whole thing at the beginning and traversing backwards. All that's a little abstract, and if you get it, that's great. Otherwise, don't worry about that. I'll do another example, and you'll see where you actually do get things being distinguished. And then we'll stop for some questions. If all the nodes of the dependency graph are connected one to another, and there's at least one final state, so there's one thing that has an X in it, then all the other states are going to be distinguished. And we'll do an example like that, where all the states are distinguishable. Let's see. Okay. Okay, here's another example. Okay, here's a finite state machine. And I think in this example, what I'd like to do is do the dependency graph simultaneous with this. So we see them both be constructed, and we'll have a whole picture when we're done. And I'll try to keep it very neat so everybody can follow. But I need you guys to help me construct it. Number one, because it'll keep you concentrating. And number two, it'll stop me from making any careless mistake. So here's what we're going to do. We're going to start off by creating a set of nodes here that represent distinguishable pairs. So what are in that list? What are distinguishable? Final states are distinguishable from non-final states. So I get AE, BE, CE, DE, and same thing for Fs, right? AF, BF, CF, and DF. Those are all the states that are distinguishable to begin with. And if I put them in this picture, where do they end up? I'll put X's in this picture on these pairs. Where are they? Yeah, so describe it for me. Help my brain. Down the F column. That's what you said.
ABCD down the ABCD down the F columns.
Now what? Is that it? 8 out of 8? Thank you, Chris. Okay, good. So in the dependency graph, it's just 8 isolated nodes, and they all have X's on them. I'm going to X them. I think this kind of masks what's going on, and this shows it. It's really a graph searching problem, and this makes it seem magical. All right, what do you do next in our algorithm? You go to the AD pair, and you check how it depends in this graph. What does it depend on? So let's throw the AD in our picture. Put it up here if it fits, AD. What does AD depend on? On a 0, it goes to B and D. So it depends on the pair BD. Is BD in here? No. It's out here. BD. And on a 1, it depends on CD. In our algorithm, what do? We basically just looked at a piece of this graph. We noticed that if there were x's here, this should get x'd. But there weren't x's here. Now, there might end up being x's there later as we look at the rest of the graph, but we haven't seen the rest of the graph yet. So we're going to have to remember that if they got x's here, we have to propagate those x's back against the arrows. So we look in BD and CD, and we put in each one of those AD. Okay? That's how we remember. That's our backtracking mechanism. And now we move on to AC. What does AC depend on? On a 0, it goes to BF. Well, for the first time the whole day, we actually got a success, right? AC goes to BF. B and F are distinguishable on the empty string because it's a final and a non-final. AC is therefore distinguishable on the string 0. Getting a 0 from C, you accept. Getting a 0 from A, you don't accept. You can't possibly have those be the same room, where walking out the 0 gets you into the treasure, and walking out the 0 from this other room doesn't get you to the treasure. They're not the same room. So these have to be distinguishable. So AC gets marked. In my dependency graph, I can still put the line in. Where does the line go? BF, which is, oh, I promised it would be neat, and I lied. It'll be as neat as I can make it. AC goes to BF. Now, in this algorithm, we don't bother checking the 1 once we get a distinguished state. If it's distinguished on the 0, fine, we're done, go on. But to complete the dependency graph, we really should check the 1. And AC on a 1 goes to CD, which is here. in the algorithm, we would not go ahead on the CD line and put AC, because AC's already been X. There's no reason to go ahead and add it there. And if you're saying, hey, what if I had looked at the 1 first? Well, then you would have put it there, and that's the way it goes. There is some arbitrariness to what order you do this. All right, how about AB now? All right, somebody who is on this side of the room. BE. Good. BE and a 0. Oh, but look, BE are distinguishable. What are we doing now? AB? You said it goes to BE? BE is distinguishable. There's an X. It connects. So AB, therefore, gets an X. What about the 1, just for completeness, Sharon? Where does the 1 go on an AB?
To CD.
Back here. Good.
There's no reason to check it, is there?
No reason to check it. No. Except that I want to make this whole dependency graph complete when we're done so you can look at it and see what it means. And then
we should be Xing AC and AB up there, right? According to our... In the graph, according to what we have established syntactically.
We can't exit yet, no.
No,
Where?
AC
you
and
have
AB.
X'd in the diagram on the left, so X the nodes in the graph, AC and AB.
So AB and AC.
I X'd AC.
But you go over to the graph itself.
Oh. Thank you. Thank you.
Go back to the arrow and exit.
Who was that woman? It's like the Lone Ranger. It's like the math Lone Ranger. Where's Tonto? They don't have Tonto in this decade. He's like, write him out of the script. Not politically correct. No Tonto. What's he talking about? Where am I up to here? BD, we're up to here? Okay, let's look at BD. BD, what does it depend on? It depends on DD, right, which is an automatic indistinguishable. And it depends on DE. DE is X, right? So BD gets X. Oh, sorry. Look at that. I'm glad we do, because as you can see, this X back arrow has to propagate back to this. If we had seen the graph, you can just see, oh, we'll go back on the arrows and propagate. But we're looking at this graph in pieces before we saw all its connectivity. That's what this funny picture represents. So we remembered that if BD ever gets an X, we remembered that over here, go back and have AD get an X. So this gets an X, this gets an X, and I crossed that out, I did it. Everybody okay? So this is a very different example than the last time. In this example, everything's getting distinguished. It's a distinguished example. BC now. I don't have BC up there, so I'll put it up. What does BC depend on? EF? Right? EF? EF's not even in here, right? So let's EF. And what else? And DD. Well, did we do EF yet? No. So over here we put in BC. Remember, if EF ever gets an X, propagate it back. This is kind of a funny way and very subtle way of storing a graph as you see it and doing one thing with the graph. Transmitting all the X's in it along back arrows to any place they can get. CD. CD depends on DF. Is that true? CD depends on DF. And what else? I know it doesn't matter. And DD. So it's not no other arrow in our dependency diagram. On a 1, it goes to D. On a 1, it goes to D. On a 0, it goes to D and F. Now, D and F is X'd, so therefore CD gets X'd. Oh, this was already... So CD gets X'd. Now, is there anything in the algorithm that's going to stop us from taking this AD and going back there and trying to X it? Nothing. We're actually going to go back there and re-X this. Okay, and that is inefficient, but there's no way of avoiding it. It's not worth looking there to see if there's an X and then saying, okay, now I won't put an X in there. All right, so don't do that in your programs ever. You might as well just put the X in. It's faster than looking there to see if there's an X and asking a question. We'll analyze this complexity-wise later and show you that that doesn't affect the complexity much at all. So don't worry about that. We only got one more left, EF. EF depends on itself. So we're done. This stays indistinguishable. This stays indistinguishable. That means E and F can collapse into one state, and they should. It's like amoebas. That's the ugliest thing I ever saw. Just rewrite it. I just like the amoeba analogy. EF it's called. It's a final state. So that collapses. And then there's two other things that collapse. B and C. They're the same.
It just becomes a line state.
Oh no, I lost it. Oh crap. BC 0, 1. Is that it? Hold on. I don't want to lose it. There. I'm just double checking. I think that's it, right? Okay. So now look at this machine that's minimized. What does it do? It's a lot easier to analyze now that it's been collapsed. You can have any symbol to start with.
It's every string that doesn't have a 1 in the second position.
Every string that doesn't have a 1 in the second position. If you have a 1 in the second position, you die. Okay. That's the minimum machine for this. Okay. Look at this picture. We started out with a graph that you didn't see the whole thing. Now the whole thing's up there for the most part, or at least the part of it that we needed. There was a beginning of this graph where some of these nodes were x'd. We wanted to transfer their x status to anything that they had back arrows to. And we did that as we went along. And now that we're finished, and there's no more arrows to put in this graph, we are finished looking at all the dependencies. What do we have? We have a bunch of x's that traveled all the way backwards and got all these x'd. And then we had a small piece of the graph that was disconnected from this piece, that are dependent on each other, but don't get dependent on any of the x's. And that piece of the graph represents states that were indistinguishable one from another. So this is really a graph searching problem. It's really algorithms. It's really discrete math stuff in disguise. It really has nothing to do with what looks like a dynamic programming table. So this is kind of a red herring here. This makes it look like something it isn't. I want to analyze how long this algorithm takes, and we'll stop for questions. You know that if you just describe this graph and traverse it, it has n squared edges, n squared, 2n squared edges, and it takes 2n squared time to traverse the graph. But that's not exactly what we're doing. We're using it in this format. So let's analyze the complexity of this algorithm particularly. How many boxes are here in terms of the number of states that we started with? N choose 2, about n squared over 2. And we look at each box exactly how many times? On the way down, one time on the way down. So that takes How many steps for each box? All you do is look at a 0 and look at a 1. So altogether it takes n squared to get through this. But there's this backtracking. Right? Doesn't that add extra stuff? Well, it does, but how much extra does it add? When you get backtracking, say from here, say this got x'd. You backtrack to the BC, you'd x that. Say that as something you backtrack. You backtrack there. Doesn't it seem like the worst thing that could happen is that you have to backtrack at every single step? And when you backtrack, you might actually go through n levels, backtracking up at every stage. That would make it n squared times n, or n cubed. You buy that the worst case could be n cubed? Well, it's pretty bad. It's pretty worst case, but that case is never going to happen. It's a very, very careless analysis. How come that never happens? How come you can never have backtracking go all the way back at every single stage for every single value?
So if you already backtracked on one cell, you never have to redo that further down.
Right, every time you backtrack, you kind of X things out, so you never ever have to X them out again. So let's ask ourselves, not from the point of view of we're starting here, we have to backtrack, how many might we have to backtrack from, but from the point of view if you're sitting back here empty, waiting for someone to send you an X. Oh, I hope I get an X, then I'll be distinguished. You're sitting and waiting and waiting and waiting. You're sitting there. How many times is somebody going to possibly visit you? What's the worst that could happen? No, not once. You might get visited twice. Okay? Every single square that's waiting might get visited 2 more times. So it's impossible for every one of these to backtrack all the way through, because that would take n cubed steps, and some of these guys would end up getting visited more than twice. The worst that's going to happen is one of these guys is going to get visited, that every one of these guys is going to get visited twice more after it's empty. Total number of times, how many times does each square get visited? In the worst case, 3 times. So the worst this really takes is 3n squared. 3n squared over 2, actually, because it's half. So this is really an n squared algorithm. I don't know which way Heather learned originally. She mentioned she learned a different way. But a way that's often taught, which is simpler to describe than this, but that really is order n cubed in the worst case, works like this. You start out drawing the graph completely, all the circles. Not just little pieces of it, but draw all the circles and X out the final states, non-final states. And then look at all the single edges and propagate the X's. And then look at the graph again and look at all the single edges from there and propagate the X's again. What you end up doing if you do it that is you look at all the vertices n different times. So n squared vertices n different times. That really does take n cubed. And that's a really inefficient way to traverse the graph. But you got to, it's not that way.
Wasn't it? We didn't draw any graphs.
Do you remember what you did?
Yeah. Remember? Show you real quick?
I sure do.
I don't know what that looks like. Basically, you just draw like a little chart where you group. You start by just grouping all the accept states and all the non-accept states. And you sort of,
It's tricky.
This is the most complicated part. And then you just say, okay, from A, do I stay in the accept states? Do I stay in this group, or do I go out of this group? And for A, so we don't have the original graph up there anymore. In A, you stay in both times. And then with B, on a 0, you went to E. And on a 1, you went to D, so you stayed in. And I think C is the same way, except it goes to F. And D stays in both times. And E and F just stay in, so they stay accepting. So then you redraw this little thing. And this time you regroup by what's alike. So A and D are alike. And then since both B and C go to this group on 0, and stay in that group on a 1, they get their own new group. Now this time, A goes to B on a 1, or B on a 0 and C on a 1. And D just goes to itself. So it stays in that group. B and C both go to D on a 0, and they go to various except states on a 1. E and F stay there. And then you draw it one more time, in this case.
Just A and D now.
Yeah, just A and D get separated. So basically, whenever you get down to one state in any group, you know you're done. You can't split the group up anymore. And as long as everything in a group is doing the same thing, really you should go through again and make sure that this splitting these two doesn't split anything else up. So yeah, but it's...
If you do it one more time just to make sure that nothing changes, then you're stable. Then you've reached a fixed point.
Yeah. So you're stable when you either have all groups of one element, or when everything just stays the same.
Good. That's a very good way. Thank you. She's brave, huh? I don't have red hair, that's the thing. Oh, I do. Thank you, Heather. That's really good. This actually is a super alternative, and it's very intuitive. The idea is that these classes are getting refined. They start really big, and you break them apart into the smallest pieces you can. But what's really good about this is that this is the basis for the solution to the triple extra credit that I gave you on the problem set. On the problem set, I say, this takes n squared time, and there's a way to do it in n log n. Okay? Now, there's no way to fix this to be n log n in any obvious way, because the graph itself has n squared nodes. Just touching it takes n squared time. You can't do anything in n log n with it. So you got to have a completely different point of view to make it n log n. And this is the basis for that other point of view. The idea is not to actually store pairs of things explicitly, but store things as groups of partitions and then refine the partition. And then the issue is, which one do you work on next? You got to work on the one of the right size next. It's not obvious how to make it n log n, but this has potential to be made n log n, and this really doesn't. Okay? At the same time, this is the one that's shown in the Hopcroft-Ullman textbook, and this is the improved version that I think it's by a paper by Hopcroft and Ullman showing that it can be done in n log n. So you can see both by the same people. You could actually look up that paper if you wanted to go read the solution to that problem. It's really a hard thing. If you figure it out on your own, great. Super. Thanks. That's a very different way, and it's a good way. OK, I have another example that I think is really illustrative, but I think I've done enough, and I'm bored of doing these examples. You probably are too. So I'll have Dimitri kind of review this example, because I think it's illustrative, and I want you to see a lot of backtracking. In the example, the last example, you can see backtracking that really goes a long way. But for now, I want to switch gears and talk about something else for the rest of the day. What questions can we answer about finite state machines, about regular sets? What questions can we answer about regular sets? Sometimes this is called decision algorithms. It's really just algorithms that answer yes or no, but the inputs are actually binary strings that represent finite state machines. So I give you a finite state machine, and I might ask you, does it accept an infinite number of things? I give you a finite state machine, and I might ask you, does this finite state machine accept any string of length 10? I give you two finite state machines, and I ask you, do these accept the same language? I give you two finite state machines, and I ask you, do they have anything in common that they accept? These are all questions about finite state machines. Questions that you would write an algorithm for, a program for, and the input to the program is a finite state machine. Maybe the most obvious question you might want to ask about a finite state machine, and the one that's done most commonly with a program is, here's a finite state machine, here's an input string to the finite state machine. Does it accept that input string? Yes or no? Okay, you could write a program for this. If a beginner in computing class can write a program for this. You can set up a little array. There's a lot of ways to do it. There's a built-in utility in Unix that does this. It's called lect. You basically describe your finite state machine, you give it a string, and it tells you whether it accepts it or not. It does a little more than that too. Dimitri's going to talk a little bit about that Unix utility. So the answer is, what questions can we answer about finite state machines? Almost everything. I'd say everything. There's hardly anything, nothing you can't answer. You can say everything. All right, so let's do a couple. Let's do a couple. Let's do number one is the membership question. I'll say what that is in English. It's one of the ones I mentioned just a second ago. You're given a finite state machine. You're given a string x. Is x generated by that finite state machine? Okay. Is x in L, where L is a regular set? So you're given two things, the finite state machine and the string. Does the finite state machine accept the string? How do you write an algorithm to do this? Just describe it to me. What would you do?
Set the machine up and run it through.
Okay, so how do you set the machine up? You need some kind of data structure. What do you use?
Graph.
Okay, you could use a graph. You could also use some kind of multi-valued array where the states are the indices, and then you can have 0, 1, and then the values inside are other states. And then you just go to the row you want to see what next state you're in, and then you set that to the current state, and then you check if it's in the final state. It's not too hard a problem. So you can do it. You can write a program.
You can do it with matrix algebra, can't you?
Yeah.
Is there a transition state for a finite machine? You just multiply.
Yes. Yes. You can do that, but that's a little tricky. I mean, you're kind of implying that it's obvious, and it's true you can do it, and I'm not sure everybody would immediately see that that's true. You can change it to a matrix algebra problem, which is also computable. Okay, here's another one. Two finite state machines, are they equal? So here's the membership question. This is the equality question. I give you two finite state machines. I want to know if they accept the same language. Do they accept the same language? Do they accept exactly the same strings and reject the same strings? How do you do it? Say it? Minimize them both. Okay, so I got two machines now. They're minimized. Now how do I decide if they're the same?
Just see that each of their states points to this equivalent state, next state in the two things.
Okay, so
Just look at it.
you just look at it, right. So here, okay, I minimize them both. So here's one machine. This is labeled, these are being input to computers. So the states have some kind of ordering. I'll order the states. This is called state 1, state 2, state 3. And here's another machine called state 1, state 2, state 3. Forget about the zeros and ones for now. Let's assume they're just here. 0, 0, 1, 0, 0, 1. Doesn't matter. They're the same. If you compare these directly in order, 1 to 1, you'll get a match. 2 to 2, you won't get a match. You'll say, oh, gee, this is not a final state. This is a final state. And if you just naively compare the machines as they're given to you, you're going to say these are different, even though they're the same. Right? Because you're given these states in some order, and if they don't happen to be given to you in the same order, you don't get lucky. This is called the graph isomorphism problem. Somebody gives you two graphs, and the question is, do they look the same? And they might be, relabeled in a different way. So how do you check if they're the same? What do you have to do to check if these are really the same then? You got to relabel them with every possible relabeling and see if one of them actually comes up with identical arrows. How many relabelings are there in this graph with n states? N factorial. Right. So whoever gave this idea, great, it definitely works. All we care about is whether it's decidable or not, whether we can do it. But as far as efficiency goes, this method, it's bad. It's definitely exponential. So is there any better way to check if two finite state machines are equal that doesn't take exponential time? Heather, you got an idea?
Yeah, I'm not sure if I'm going to remember it quite exactly, but something like you take the union of the intersection of the first with the inverse of the second, and the intersection of the second with the inverse of the first.
Right.
And end up with
Yeah.
Isn't it an analogous problem to this one, and just see if they're equivalent to one another by doing the same kind of thing, sending strings through and seeing if they end up in the same states?
I don't know. I'm not sure exactly what you mean. You want to take each machine and run it through here, but then we'd still have to relabel the letters to see if some relabeling would match the x's up precisely.
Right.
Right?
I'm thinking that all you really care about is that every string ends up in an accept state or doesn't.
Okay. Oh, I see. So use the same kind of... I'd have to think about it for more than the 30 seconds to kind of come up with an idea like that. Maybe is the answer. I don't know.
We're talking about deterministic finite state machines, right?
Yeah. Well, you can always... Yeah.
So I guess I'm not sure why we need to try factorial relabelings. Why wouldn't you just start at the start state and then,
The start state is the only state that's uniquely identified.
Right.
But all the other states could be labeled different things. So the state labeled number 2 might not be the state that's labeled number 2 in the other machine.
Right, but how you get to state number 2 is either by a 0 or a 1, right? Which is unique.
I suppose that's true, right. So if you could start at that initial state, if you see a 0, you can just relabel it yourself.
Right.
I agree. So that's a good idea. Seth basically says that we don't really have to try all n factorial labelings. We can start from that initial state, which is identified, and use the deterministic aspect of it to relabel it ourselves in the only way that's possible. I'll go for that. I'm willing to go for that.
Relabel them both with your own.
Relabel them both with their own label and check for consistency. 100% good idea. Good way to fix it. But I know everybody was laughing when Heather was giving her idea, except for the fact that she didn't mention you're supposed to do a handspring at the end. She's right. She has a very good idea, but it relates to a lot of other problems that you can solve in a similar way. Seth's idea is excellent, but let me go through an idea that's equivalent to what Heather was saying, but won't seem quite as complicated, I don't think. If two FSMs are equal, let's call them A and B. Then if you calculate their difference, what should that equal?
Nothing.
Should equal nothing, right? If you take away all the strings in B from all the strings in A and they're equal, then you should get nothing. Now how do you calculate A minus B? I can make a finite state machine equal to A minus B. A minus B is the same as A. Who knows how to do A minus B from set theory? Symmetric difference of a set. A intersect not B. That's A minus B. So take A, take B and complement it. Intersect the two. This represents A minus B. Do this, do the complement, intersect the two, minimize it. If it looks like this, you're done. The answer is yes. If it doesn't look like it, the answer is no.
Don't you have to go both ways?
What do you mean both ways?
Like also do B intersect inverse of A?
I don't think so. I think if A minus B equals the empty set, then we're okay. I don't think you have to do both. I'll think about it, though. Maybe I'm wrong. Maybe I'm wrong, but I think this is enough. But this idea of going back and using set things to create new finite state machines and then minimize them is a very commonly used tool in doing these kind of decision algorithms. And you can pretty much decide anything you want about two finite state machines using these kind of tools. Let's see. Let me do one more and then we'll let this topic go. All right, how about this? How about the language is infinite? Somebody gives you a regular set, and you want to know if the language is infinite. What do you do? Look in your finite state machine and see if there's a loop. Who's betting the farm on that? While we wait to see if we bet the farm, Chris can figure out exactly what it is that's subtly wrong with what he said. What's wrong with what you said? Why isn't it enough just to look for a loop?
That leads to a final state.
Right.
There's got to be a loop on a state that has some path that goes to a final state. There can be plenty of loops elsewhere that might not make it. So you look in your finite state machine, and you look for cycles. And it doesn't have to be a loop. I mean, you meant a cycle. You look for any cycle, and if any node on that cycle has a path to a final state, then you say yes. So again, you're back in graph algorithm territory. There's a lot of stuff that relates to that. There's other ways of doing this. Why don't you just turn it into a regular expression and look for a star? That's pretty safe, right? I think it's easier to think of this with a regular expression than with a machine even.
For equality,
Mm-hmm.
no, because they can come up different.
What?
You turn them both into regular expressions and see if they were the same, but
No, but I'm so glad you asked that question.
there's even more regular expressions to describe something than there are.
There is no minimum regular expression, and what's worse, the problem of determining whether two regular expressions are identical is NP-complete in the size of the regular expression. It's a hard problem. The only way we know how to do it is to convert the regular expressions to NFAs, back to DFAs, and do it the way Seth said. So regular expressions are very hard to deal with. Almost every problem about regular expressions with respect to the size of the expression is NP-complete. There's a whole list of problems about regular expressions that are NP-complete.
Sean,
Yeah.
there's no minimum just because when you do the conversion, you can take the nodes out in different orders. So you can end up, I mean, that's sort of, because I can have a minimum finite state machine. I can convert a finite state machine to a regular expression. But there's more than one way to do that.
There's more than one way to do the... I see what you're asking. Yes, Michael. Right. Depending on which state you rip out first and what order you rip them out, you will get different regular expressions.
That might have the same length.
That might have the same length. That might look different. Absolutely, yeah. Yeah.
Heather's right about both sides.
You need to do both, huh?
Like if B is larger than A?
Yeah.
Then
If it encloses A, then you're going to get empty. Right. Right. So Heather's right. You need to do this to check A minus B equals empty and B minus A equals empty. Because A minus B can equal empty whenever A is smaller than B, whenever it's contained inside. You're 100% right. So you need to do both, and that means you got to do two sets of machines and see if they're both equal to this.
With an optional handspring.
With an optional handspring in between, right. Now, this isn't so bad to do. Right? Complements is an easy thing to do, and intersection is not an exponential process. It's just a product, like Dimitri showed you last time. So these aren't so hard to do. You can do them efficiently. What else?
That way it's just a simple
Yes, because you know what to fix on, and you have and it's deterministic, so, and you know the edges are there, right? All right, how about this? How about is regular set A contained in a regular set B? So you get two regular sets. Is every string that A accepts also accepted by B? B might accept more, so it's kind of like that equals, but is B bigger than A? Is B contained in A? Should I leave that one and then you'll think about it and talk to Dimitri about it in recitation and eat lunch in the meantime?
That's just equivalent to doing one of these unions and
Yeah, is it?
or intersections with complements.
A contained in B.
Then if we look at B minus A and
Mhm.
A minus
A minus
B
B
will
having
be
an
empty set and B minus A.
Do you want to talk about this today or not? You don't have to.
There's not that much to say.
There's not much to say. I do want to say this one thing about it. What Chris is saying is pretty much right, but I want to just remind you of one little discrete math thing. You know how intersection is like
A box of chocolates.
intersection is like binary multiplication, and union is like binary. Intersection's like and union's like or, right? And complement's like not. What's this like? What is this like? That's true. It's like implies from logic. X is in A implies X is in B. A implies B. Remember how to convert this to nots and ands and ors? What is this? Who remembers? Oh, nobody remembers. All right. Not A or B. Let's do that with sets here. The complement of A union B. What's going on? If you calculate the complement of A, is it union? Yeah. Union B. If you calculate this, that represents somehow this logical statement that A is contained in B. If this equals everything, if this is true for all the strings, if this equals sigma star, then A is contained in B. So I want to point this out just to go back, and the logic and set connections all come back and give you a lot of power if you can remember them and use them. This is another way to do this problem. Calculate complement of A, union it with B, and then you can set it to the single equality finite state machine that accepts everything. And we did equality before, so one decision algorithm builds on another. Last line before I quit today. Decision algorithms, we really care about whether they can be done or not. Is there an algorithm that answers yes or no? We don't usually care so much about the complexity unless we're really implementing it. The reason that is, look, we really do care about complexity, but the reason that we focus more on whether it can be done or not is because the minute we're up to the next level of machines, push-down machines, and context-free grammars, almost everything you want to know about them, you can't know. Forget efficiently, you can't know it at all. If I give you two context-free grammars, and I ask you, are they the same? Do they generate the same language? Undecidable. You give me two compilers in general, and ask me, are these two compilers doing the same thing? No way to write a program to check that. You give me two compilers and ask me, is there anything in common between the two that they accept? No way to do that. The only thing you can do for the next level is the membership problem. And that's actually compiling itself. Give me a grammar, give me a program. Does the grammar generate the program? Yes or no? That's compiling. That you can do. Nothing else. You can't do anything else. Well, one little thing. You can hardly do anything.
So what's an example of an undecidable finite state machine?
There aren't any undecidable questions that are interesting about finite state machines. Everything's decidable about finite state machines. But there's lots of undecidable things about the next level. And when you get up to Turing machines, there's essentially nothing interesting you can decide about a Turing machine.
What a fascinating topic to talk about.
There's actually a theorem. It's called Rice's theorem. It says that any non-trivial property of a Turing machine is undecidable. And then they define what non-trivial is. A trivial property of a Turing machine is how many states it has. That's decidable. But anything interesting about a Turing machine is undecidable. Anyway, all right, let's quit here.